The following are a number of questions that may be on the lab test or term test version 1 or both. So you're going to get adding binary numbers, and it's going to give you numbers like this one plus this one, and then you have to figure out what is the answer and what is NZVC. Now what we can do with the calculator here, because you're allowed this in the lab section, we're going to go to binary, and we're going to put in this first number here, 1101, 1011, and we're going to add to that 1110, 1101. And our answer here is this. Now this is going to be our 8-bit answer here. And let's compare it to all the answers that we've got here. So this matches, this matches, this matches, this doesn't match. So right away we know that this has been eliminated. Now when we add two 8-bit numbers and get an extra digit, that digit is the carry bit. So carry is going to be 1. So we've got this one or this one, and we know that this is not true. So it's either going to be A or C, because we've eliminated B because C is not 0, it's a 1 as we can see here, and this number is not the right answer. We can see here that this answer here, most significant is 1, which means n equals 1, that's not helping. We also know that z equals 0, so this value here is not 0. So it really comes down to the V bit here. So this is a negative plus a negative, giving a negative. So if you add two negatives and get a negative, V should be 0. So C equals 1 and B equals 0. It should be answer C. This is what the right answer should be. This next question goes through a binary subtraction. And again, what we can do is we can clear results from the previous calculation. And we can punch in these numbers, 1, 0, 1, 1, 1, 1, 1, 0, subtract 1, 1, 0, 1, 0, 1, 1, 0, and equals. Now, our 8-bit result is really these last 8 bits here. All these extra ones over here means that we had to borrow. We need to borrow if we subtract a larger number, which this is, from a smaller number, we have to borrow. And every time that happens, we'll get a whole bunch of ones preceding it, which is really just saying the carry should be set. Now, our number is 1110, 1000. And I can see that all of these numbers are identical, so that doesn't eliminate anything. And n equals 1, again, because it's negative, so that doesn't help. And these are not 0. So we have to have the carry equal 1, so it's either going to be A or D. It can't be these two because it carries 0. And the only difference here, again, is the V bit. Now, if we look at these numbers, this is a negative, subtract a negative. Figure it out, we can change this to an addition by saying negative subtract a negative is the same thing as a negative plus a positive. If you add numbers of opposite sign, you cannot get a signed overflow. So of these two that it could be, B is 0. So it has to be this one. So the answer has to be D, because it's negative, not 0. There's no signed overflow because a negative subtract a negative, same thing as negative plus a positive, which does not give you an overflow. And we have all these extra 1 bits indicating that there was indeed a borrow in this case. The next question says, when you subtract a smaller number from a larger number, you get an unsigned overflow. And think about it this way. If you have $20 and what you want to buy is only $10, you don't have to borrow. And borrowing is when you get an unsigned overflow. So if you subtract a smaller number from a larger number, you're not going to get an unsigned overflow because you don't have to borrow. It means that this is false. Now this question says when you subtract numbers of the same sign, you get a result of opposite sign, and you have a signed overflow because of that. And think about what the real rule is. It says if you add two positives and get a negative, or add two negatives and get a positive, that's when you get a signed overflow. Now when you subtract, let's take a look at subtracting two numbers of the same sign. A negative subtract a negative, as we saw earlier, is the same thing as a negative plus a positive, which in that case is you do not get a signed overflow. If you have a positive subtract a positive, that's the same thing as a positive plus a negative. And again, you cannot get a signed overflow. So this question, the answer is false. Now in this question, we have a number of binary numbers, A, B, and we're doing exclusive ORing, ANDing, ORing, and inverting. Now, if you're doing this on a lab test, you still have the PC calculator to figure this out, but you also have Kyle Studio Cloud, which means you can type in this program and figure out what the answers are, because it's going to tell you what these various variables C, D, E, and F are in a hex format. Now, it won't allow you to see it in a binary format, so even though the answers are going to be binary, you should be able to easily convert what it's showing you here in hex to binary and making sure that that's the right answer. So here are all our possible answers here. And again, we can bring up our calculator here to help us out with this. And the first one is exclusive OR. If you remember, exclusive OR means that the two bits are the same. The answer is 0. If the bits are different, the answer is 1. To be exclusive, you have to be different. So C is going to be 0, 1, 0, 1, 1, 0, 1. 1, and that's what C should be. Now D is going to be A ANDed with B, and if you remember that ANDing, both have to be a 1 to get a 1, otherwise you get a 0. So this is going to be 1, 0, 1, 0, 0, 1, 0, 0. That's what D is going to be. Now E is A ORed with B, and the only way you can get a 0 is when both of these are 0, otherwise you're all going to get 1s. So in this case, 1, 1, 1, 1, 1, 1, 1, 1. So you're basically getting FF in hex. If you look at F, which the inverse of B, which means that every bit here is going to be completely inverted, which would be 0, 0, 0, 1, 0, 0, 1, 0. And therefore, you should be able to figure out what the answer is. So each one of these is FF, as we saw before, but when you work it out, I think you'll find that the answer is C. Now again, we can use the programmable calculator here to figure this out, but one thing you cannot do in the lab test is you're not going to be allowed a pen or paper. So one of the things you can do is if you want to do these kinds of scratchpad things, you can't use Notepad or anything like that, but you can go to Kyle Studio Cloud, put in a comment area in one of the programs and do your rough work there. In this question, it says, to make the contents of a printf go to the screen, what other statement do you need? Now, if you take a look, standard out sounds pretty good because that's going to the screen. Standard in and standard in are definitely going to be wrong. But the problem that you run into here is this is not the right command. Notice we got flush standard out. That's not correct. I think it is, but it has to be F flush standard out. So this isn't right, this isn't right, this isn't right. So the answer is going to be none of the above. And how can you tell that? You can actually bring up Lab2A out of Kyle Studio Cloud, and you will see that it actually says F flush, but not standard in. It says F flush standard out. So your programs that you've got already in Kyle Studio Cloud are a way to look and understand stuff and double check things. Remember, you have 90 minutes to do about 10 questions. So you've got lots of time to look over anything that you've got as programming in Kyle Studio Cloud. As we saw in the last one, you would even have enough time to type that program in and see what the values are in hex and actually say, now what are those in binary, and figure it out that way because you can't use a pen and paper in the lab test. MBED, we have 3 different versions of the MBED operating system. We have MBED OS 2, MBED OS 5, and MBED OS 6. And again, we have programs, if you look at Lab 2, that use MBED 2, 5, and 6 to do basically what we had, where we're typing characters in from the keyboard and having them go to the screen. Now the \n would be in a printf, and a printf is a new line, which means it goes on whatever line it is and goes to the start of a new line. Now the way it works is this. MBED OS 2 and MBED OS 5, if you look at Lab 2A that have MBED OS 2 and 5, you'll see that when you hit the enter key is really a carriage return. What does a carriage return do? It puts you back to the start of the same line. And it says in the code, if it is a 0x0D, which is a carriage return, put a line feed to move you vertically down. And so \n for MBED is formed by a carriage return, which puts you back to the start of the same line, plus a line feed to move you to a new line. So there is a typo here. It should say the \n, which is again new line. For MBED is formed by a line feed in MBED OS 6. Now, if you remember again, the version for MBED OS 5 and 2 was a carriage return for the enter key. But what you're going to find that for MBED OS 6, the enter key in MBED OS 6 is a line feed, which is a 0x0A. So that's all you need is a line feed in here for a quote \n. So this is indeed true. Now this question says, which of the following definitions works to associate the name LED with the blue LED on any MBED board, including the Freedom K64? Now, some of these look really good, but the one thing that you have to remember, and you can see this by again looking over your programs from lab number 3, DigitalOut starts with a capital D, and the out has to have a capital O or it won't compile. Because LED 3 is indeed your blue LED, but DigitalOut is not properly spelled here. This has to be a capital O, so you can eliminate this one right off the start. DigitalOut LED lead 2, that doesn't work because lead 2 is actually your green lead and it asks for a blue lead. DigitalOut, capital D, capital O, that's fine, lead. And there's two versions of all of these. Lead 1, lead 2, and lead 3 are red, green, and blue. But you can also say lead underscore red, lead underscore green, in this case, lead underscore blue. So this is our answer here. Now it says to have the left push button assigned the label PB you would use. Now the left push button, if you remember, is indeed SW3, but the push button is an input, not an output. LEDs are outputs, push buttons are inputs. So DigitalOut is definitely wrong here for this. Now you got capital D, capital I, so that's fine, PB, but SW2 is the right push button, and you want the left. Now you got DigitalIn, PB, SW3, which is right, except for one small detail. It has to be a capital I, so the answer here is none of the above. And again, you can look at your code in Lab 3 to figure out which one this should be because you have program statements that actually have things like DigitalIn with the capital I's here and SW2 and SW3 and hopefully comments that you can look at during your lab test. Now, in this question, it says when a push button on the Freedom K64 is pressed, the value will be a logic 1, which is equivalent to 3.3 volts. Well, if you look at the diagram here for both SW2 and SW3, one of the things you're going to find is that you have a push button here when it's not pressed. You're going to have 3.3 volts going to the microcontroller, which means it's a 1. So when it isn't pressed, you're going to get a 1 logic level and 3.3 volts. When you do press it, it's going to then have ground coming out on here. So not pressed, it's a 1, pressed, it's a 0. Answer to this question here will be false. Now, even though A to D, which is on Lab 4, is not part of Lab Test 1, questions from that will be on your Term Test 1. So you're going to have to know about these sorts of questions for Term Test 1, but not Lab Test 1. Now it says, which of the following statements will associate the label ABC with the temperature sensor? And again, the capital A here for analog and capital I, AnalogIn. But if you remember, A1 is the pot, and that's where we're always going to connect the pot. So this one is not valid. AnalogIn, ABC, A0 seems fine, but it has to have a capital I here. AnalogIn, ABC, A0 is our correct choice. Now it says when putting temperatures on the Putty screen, you have to have CP437, which means code page 437, selected in translation section of Putty to make sure the degree symbols show up properly. Now, so far we've seen that under Putty, you have to choose the right COM port based on what the device manager says. And then we also have to say implicit carriage return every line feed and force local echo on. But we also have to go to translation, slide down to get to CP437 if we want the degree symbols to show up. And so this is true. Now again, because this will be on Term Test 1, we're covering this, but you do have some programming code already in Lab 4 that may be available. And again, the thing that you want to look at here is AnalogIn, A, capitalized, I, capitalized, and some name. And this name is now going to be associated with A0, and we know A0 is connected to our temperature sensor. Now it says temp.read. Now it could say Bob and Bob.read or whatever, but there's two basic functions for AnalogIn. One is .read, which is going to return a floating point number from 0 to 1, so this is true. And the other one is temp.read underscore U16. U16 means unsigned short, and the read underscore U16 is used to do calculations for the temperature. But if we just say temp.read, then it's going to generate a number between 0 and 1 as a float. So indeed, this is true. Now, in the past, we did have microcontrollers that were 5 volts and ground, but the Freedom K64 isn't that. The Freedom K64 actually works with voltages, 3.3 and ground. Now, what you're going to find is some of the newer microcontrollers work with 2.8 volts and ground, especially the ones that are 64-bit that you find in portable devices. So the answer for this question is for the Freedom K64, 3.3 volts and ground are the voltage levels. But then you're asking yourself, well, why has it gone from 5 volts to 3.3 and on the newer 64-bit ones, 2.8? If you look at power equals voltage times current, that means that the lower the voltage, the lower the power in the device, the less heat it's going to generate. And so things like iPads or various devices like this will have lower voltages to make sure that they don't heat up and they don't use up as much of your battery. But the answer for this, again, is Freedom K64 works with 3.3 volts and ground. It should be fairly obvious. Standard in, the input devices are keyboard. Standard out, the output devices are PC screen. So this is indeed true. Now, for a question like this, on the theory test, term test 1, you can look this up, but you can't start looking things up from lab 2 or anything like that during your lab test. So how do you figure this out? Well, the simple thing is you start running Lab 2A. If you run Lab 2A, it allows you to put text on the screen. So let's just say that we had all this stuff typed in and we use our up arrow key to move ourselves in the middle here. Then we can actually say escape, let's square bracket 1J and see what it does on the screen by just running that code. And in this particular case, 1J actually clears from the cursor to the top and 0J from the cursor to the bottom and 2J clears the entire screen. But just by running that program in the lab, that's how you can figure it out. And in our case, as we said, escape let's go break 1J clears from the cursor to the top, and that's our answer here. Because in lab 2 we were dealing with a string array, this question, all string arrays must be terminated with what character? Now quote \n really is new line. And as we saw on MBED OS 2 and 5, that's a carriage return and line feed. Quote \r means carriage return, which is the same as a 0x0d. Now, most of you have seen null as quote \0, which is what a null is as a character, but as a hex value, it is 0x00, same thing. So as we saw, there's a duality on char variables. It can be a character, such as quote \r, or it could be 0x0d. So quote \0 is the same as 0x00. So this is our right answer here. Now this question says arrays and variables are stored in. Now it gives us a number of different options here. And arrays and variables are not stored in ROM because ROM stands for read-only memory, which means you can't put anything in here. It's burned into the chip and you can't change it. So you can't store variables and data into that. Flash memory is for programs. And again, that's not where arrays and variables are stored. And arrays and variables are typically not stored in registers. So it's none of the above. Where are arrays and variables stored? In RAM. And RAM is random access memory. And that type of memory, when you first power it up, has random stuff in it. So if you declare a variable to be float, as you may have done when you were using Visual Studio in PRG 1 and 2, and you were tracing through it, right at the start, before you assign it a value into that float variable, you're going to see some number times 10 to the minus 39, which is just random stuff, because that's what's in RAM when you first start up. So there's no default value in RAM. It's full of random stuff. So RAM is the answer that we wanted here. So it's none of the above. Now this question says the color magenta can be made by mixing red and green, blue and green, red and blue, or none of the above. Now, one of the things you can do to prepare yourself coming in for these kinds of questions on your lab test is to create a very simple program like this. And how do you go about creating a new program? It's very simple. We showed you on the last lab how to duplicate a program that you already have, and then get rid of everything and then put in code like this. Now we've got DigitalOut red, LED_red, can be either LED_red here or LED1, green, LED_green, and so on. So we've specified red, green, and blue. Now, if we want to just see what green and blue is, we'd want to say red equals 1 to turn off the red LED, and we turn on the green and the blue, and then we'll see on the LED what color we're going to get, which is green and blue. And so I think you're going to find the green and blue, I think is cyan, but by running this, you'll actually see it showing up on the LED. So this is maybe a little bit of programming that you might want to do before you come into the lab test next week. Now, this question says, what does line 28 of the code do? And the code is here. Let's take a look at it. And if we take a look, we've got DigitalOut red, LED1, DigitalIn, right, Pushbutton SW2. So these are all correct. And we've got our include embed.h. And if we look down through here, this is line 28 here. Now, some of the things that you should be aware of is that your human reaction time is no faster than 1/10 of a second, which is 100,000 microseconds. However, each line of code here gets executed in a fraction of a microsecond. So the way this code works, it says forever do this stuff, and it's first of all turning the red LED off. And then it says down here, if the right push button equals 0, which means you pressed it, only then are you going to go in and change it from being 1 to 0, and then you're going to hit this statement. Now, if you don't press the push button, it's just going to bypass this, and keep it turned off. But eventually, you're going to push the button, and a quarter of a microsecond later, it's going to hit this, and another quarter of a microsecond later, it's going to hit this. And as we said, it takes you 100,000 microseconds to get your finger off the button, which is what you're doing here. So it's definitely going to have the right push button here. When you hit it, it's still going to be 0. And when you say while right push button up arrow 1, that means 0 exclusive OR with 1. and that's equal to 1. So this is a true statement. So as long as your finger is still in the button, which it's going to be for 100,000 microseconds, it's going to sit here. Now, once you take your finger off, then this is now going to be a 1, exclusive word with 1, which is not equal to 1, and then it's going to continue on in your code. So what it's really saying is if we release the right push button, then it goes on to the rest of your code. Let's see what answer that is. Waits until the left push button? No, it's the right push button, so this isn't correct. Causes an error? No, it is a proper while loop. It's just one where we have a device changing state instead of a variable. Waits until the right push button is released before it goes to the next line. I think this is our answer here. Now in this question it says, what happens if you change line 25, which was one of your lab quizzes, which I believe was lab quiz 3, if we replace the if statement with this? So let's take a look at our code again. So if we replace the if statement here with that while statement, let's take a look and see what this does again. If you push the right push button, it goes into the code. Let's take a look at what our option is here. So instead of that, we're going to say while right push button up arrow 1 is not equal to 1. Now, if we don't push our right push button, that means it's a 1. One exclusive word with 1 is a 0. 0 is definitely not equal to 1, so it's going to sit there. Now, what happens when you do press it, and the right push button now is a 0, 0 exclusive word with 1 is a 1, which is not equal to 1 is not true, then it's going to go in. So this is the one that we want here. It's going to wait for the left push button. No. Cause an error. No. Waits until the right push button is pressed before it goes on to the next line. Now, it may take a little while to sort of figure this out, but this is pretty cool stuff because it's going to sit on this line until you actually press the push button. Like the if statement doesn't go in, but it's waiting here before it goes in. So this is our right answer here. Now this question asks, using the Chrome browser for both Kyle Studio and doing your lab evaluation will cause your lab to auto-submit if you clear the browser history. And this usually is true. And what that means is we want to make sure that we have something like Edge doing your evaluation, but we're forced to use Chrome to use Kyle Studio Cloud. So this question is saying, in Kyle Studio Cloud, when you use the hammer, which is this guy here, to build a bin file, and that's what it does. What you have to do if you use the hammer, you have to drag and drop the bin file it creates into DAPLink. And then on the left-hand side of the Freedom K64 where your shield is, you push the reset button in order to run it. And it's asking, does all that happen when you just hit the arrow button? And the answer is true. This question says, for the red, green, or blue LED on the Freedom K64, a 1 or 3.3 volts turns it off and 0 volts turns it on. Is that true or false? We have two ways to hook up a LED. This way here, if you have the microcontroller hooked up here, 3.3 turns it on and 0 volts turns it off, but this is not how we've hooked up our LED. We've hooked up our LED this way, where we have 3.3 volts coming this way and the microcontroller connected here. What that means is we got 3.3 volts here, and this is 3.3, it's off, 3.3 and ground, it's on. So this statement is indeed true.